Okay, after knowing that what structure of the muscle generate the contraction and the muscle forces and how we can mathematically formulate it using the HERS model, the next step is how we can implement it to analyze the human motion. So I brought simple examples about jumping and throwing example initially examined by Alexander paper. The observation for the long jump and high jumps touchdown configuration for the runners are pretty much different to each other. Like for example, the high jumps, their speed are not that high. Instead, their touchdown angle to the ground from their center of mass to the contact point is somewhat shallow compared to the long jump. For the long jump, the runner speed is really, really high speed. I think most of the maximum speed, and their touchdown angle is pretty stiff. Okay. So there must be some benefit having that configuration for the touchdown or touchdown body posture. And what are the mechanical benefit for doing that? That's the question that has been asked. And then this is a pretty fun paper that explain or examine those differences between the long jump and high jumps and its optimality using a very, very simple mechanical model like a point mass model with a very simple Hills muscle model. That's what I'm going to introduce here. Okay, so for the hypothesis is there are some best combinations for the V naught and theta naught exist for long jump and high jump respectively. Okay, some specific combinations for the V naught and theta will give you the maximum height, and the other combination will give you the maximum distance. That's the hypothesis. So optimal here means that usually when we are doing the analysis, students or the researchers are talking about the optimal value, sometimes referring to best result from the trial and error. So suppose that you have many parameters that you can vary, and then by varying some of the combinations, you found that some of the value that will give you the best results. That's what they call optimal. But here, I'd like to say that the optimal is more likely the global minimum or maximum point of view. So for example, so in the previous chapter for the chapter 2 locomotion, we examined what are going to be the best least costly push-up magnitude for the bipedal walking, right? So as you keep increasing the P, your total mechanical energy decreases, but within some constraints, having positive hip joint work, we found some energy efficient walking conditions for the push-ups, right? So even though I say it's an optimal walking, it's more likely least costly walking in the mechanical energy perspective. So instead of having those monotonic decrease, when we usually talk about the optimal value implies that there are some local minimum exist. So if you are push harder, maybe your work getting increased again. So that the point that this guarantees those local minimum is what we call the optimal value. So with that, to support this hypothesis for the optimal takeoff modeling, we will examine what are the resultant behavior for the maximum height and distance. Like you have a two variable V naught here and theta naught here, and examine what's going to be the resultant performance. If there is any local minimum or maximum value that will guarantee those performance, here maybe this combination for the V and theta will give you the maximum height. So it's the optimal value for the performer, the runner, right? Sometimes we'll give you the monotonic trend, decreasing trends or increasing trends, meaning that the faster the better. Okay. So we'll examine if we could get those results, a conclusion at the end, using very, very simple mechanical model. So to begin with, I would like to summarize the solution steps for the jumping analysis. So again, we will always start with the equations of motion. It's mechanics problem, modeling the human motion in terms of dynamics and control. So compared to the previous bipedal model, we now have an active actuation term, right? It's not a passive anymore. So for example, like your joints generate the muscle forces and torques. And we know that those torques are generated by the muscle forces, and the muscle forces by Hills model have three different components, like a contractile element, parallel element, and series element. And those introduced the muscle length dynamics, but try to make the problem simple. We are going to assume that those relationship for the muscle lengths could be approximated as joint angles, okay, the joint kinematics. So we'll reduce the state variables for the muscle length. And we are going to integrate this up to certain event. For walking and running, you actually integrate the equations of motion up to maybe the double support phase or the takeoff phase, right? Similarly, we are going to integrate those equations of motion until the takeoff occurs. Okay, after takeoff, it's going to be a simple ballistic motion. So you can actually obtain the height and distance corresponding to that takeoff state variables. And the next step is you have to interpret the results. Is your results support the hypothesis, like optimality, like optimal combinations will guarantee the maximum height or distance? That's why we have to examine. And also, you should compare your results with the experimental observation. So are these value feasible or make sense? Okay, and also there are some assumptions you actually applied in the very beginning, and then during the parameter study, you have to check your results if those are valid. Those are pretty much the steps that for analyzing human motion with muscle activation. Okay, let's work on how we can formulate the modeling for the jumping. Okay, so let's start with point mass analysis. I know this is too simple. However, we already observed that those point mass approach can tell us about many things about walking and running. Okay, even though it's simple, they can hold some basic characteristics for the dynamics. So what if this could also true for the jumping analysis? So we are going to assume just point mass approaches. So two parameters are what we're interested to examine is the touchdown velocity, touchdown speed, and the touchdown angle. Okay. And to apply the muscle forces, I would like to add a two massless leg connecting the center of mass to the ground. So those torques applied at the middle, the knee torques is the only actuation by the muscles. Okay. Of course, there are hip torques and ankle torques. There are many other actuation possible, but try to make this simple. To make the system simple, I only added a knee joint torques. Okay, and if I set it up the model this way, the next step is the ground reaction force. What's gonna be the direction for the ground reaction forces? So we already handled this problem for Wilmer's wheel bipedal walking model. Is this force directed to the center of mass? Yes, because we assumed that a massless leg. Okay, massless leg only transfers the force from one end to the other end. So those force should be directed toward the center of mass. Okay. So assumptions again here is we are going to do the point mass approach, and only horizontal motions exist, horizontal speed. Of course, there are some in real vertical directional component, but assuming only horizontal, massless leg, and only knee torques applied. Okay, with those assumptions, we could formulate the relationship between the knee torque and the ground reaction force. Okay, so by exerting the knee torque, we push the ground, that the ground reaction force has a relationship between the active actuation with this manner. And knee torque again is generated by the muscle contraction, right? So we have such a connection between the muscle force, which is proportional to the knee joint torques, which is a function of the ground reaction force. Okay. Okay, here again, so those are the function of knee angle, okay? And those phi is gonna be also a function of theta, but due to the geometry. So if we solve those geometry, like knee angle will determine the position for the center of mass, we could formulate the relationship between the theta, phi, and the theta, which we'll use later. Okay, so what's gonna be next? So since we set it up the point mass model for the stance phase, the next step is what will happen after that. So during the stance phase, we have to just apply the equations of motion for that. But when the takeoff occurs, there is a ballistic, falling. The problem, just only gravity downward. So by solving them, we can formulate what's gonna be the maximum height and what's gonna be the maximum distance. So equations of motions are simply stand space, only external force from the ground reaction force and the gravity, area phase, only gravity. And you can just solve it up to the takeoff occurs, like a ground reaction force turns out to be 0. Okay. Once you obtain those takeoff variable, like a takeoff state, like a position and velocity, the next step is very simple ballistic motion solving. Most of us have gone through when for the high school physics. Okay, so you could find what's gonna be the maximum height and the time it takes and this total distance. So by having takeoff states, you can calculate the performance. Okay, and then examine how those are related to those initial conditions like V naught and theta naught. So next step is how we can then formulate this equations of motions, the ground reaction force in the equations of motion into the muscle mechanics muscle model. Okay, so for the muscle model, if we recall Hill's model, there are 3 components, CE, PE, and SE, and then if we formulate them, it's pretty much complicated, right? So I only consider the elastic components here for the parallel and the serial. It's pretty complicated. So should we include them all? Well, depends on what you're examining. So it's always the problem that the researchers should figure that out, like which kind of reduced model or simplified model you would take to demonstrate to support your hypothesis. So the idea is, since the muscle model looks like this and velocity has a profile like that and passive, now the elastic components look like this, which one really affects the jumping motion? Okay. My goal is to find out what are the combinations for initial takeoff, touchdown speed, and leg configuration will affect the final performance. Which muscle behavior contribute most? Which muscle component will dominate first? Since I always recommend you to the simplified model trial first, so that you can get more insight about the physics, and then if it doesn't work, you can just make it more one step further complicated more and more. I'm going to briefly introduce the terminology that's been often used by mechanics. So iso means here the same, the constant. Metric means the length, kinetic means the speed, and the ton means the force, the magnitude of the force. So isometric contraction means you make a muscle contraction with constant length, which means suppose your arm is in the fixed configuration and you just apply the force. That's the isometric contraction. Isokinetic contraction means there's a constant speed, like a joint angular velocity. So it's not really easy to control by human by themselves. Isotonic means there are constant load applied. So if you are attached to some machine that'll give you the constant rigidity force, that's kind of isotonic contraction. Okay, so for that, suppose for the running, like jumping, assuming if there is a very small change for the length, we could assume that's isometric contraction. And for the jumping, if I'm interested in the range here, so the velocity doesn't change much, and then I can just approximate, instead of having the full muscle velocity curve, I can just approximate the average value for those regions. That's for isokinetic contraction. So what's really the case for the jumping? Well, it's a really short amount of time, right? So we will assume that very rapid change for the velocity matters, force velocity relationship matters, and compared to that, the length change and its corresponding force change will be negligible. Of course, this is assumption. So we should check later if this assumption was valid. But for this, at this point, to make this problem simple, we assume that those muscle forces are approximated as force-velocity relationship only, like this. Okay. Okay, the next step is still it's a muscle force and the muscle shortening velocity. And then what we have is from the equations of motion is the joint torques, knee joint torques, and all those thetas and phis, such as a variable that describe the point mass. Okay, so we assume that Since this is really simple massless model with a single joint, your knee joint will be proportional to the force, of course. Okay. So we assume that those F function, like force velocity relationship, will be also hold for the torque shortening velocity relationship. So maybe the torques will have a similar configuration relationship. Okay, again, so for muscle shortening velocity at the knee will also affect the knee joint angular rate, right? So for this simple example, we could also assume that those length rate change will be proportional to the angular knee joint angle change. So by having those assumptions, we could formulate those torque and joint angle relationship as a form of reciprocal function as similar to the force velocity relationship. So plug that into the original equations of motion like that. Okay. So this how we can obtain the equations of motion in terms of muscle mechanics. So to summarize the solution step for the optimal jumping, the very first step is the equations of motion for the jumping. For the stand space, we will have only external forces, the ground reaction force and the gravity. Area phase only ballistic motion by the gravity. And this force, again, is now going to be a function of muscle force. So from the Hills model, only highlighting the force velocity curve, we express it as in terms of torque and the joint angle, knee joint angle. Okay, and there are some parameters involved with those modeling. Okay, so until when we are going to integrate them? So we are going to integrate them up to the takeoff state. So takeoff state is usually the phase where ground reaction force turns out to be 0. So that's the case where either knee joint torque is going to be 0 or leg fully extended. Whichever comes first, you stop integrating the equations of motion. In MATLAB, take the event on and just stop the integration and then just obtain the value for the takeoff. Okay, at this point, do you wonder why there are two conditions exist, like a knee joint torque equals to be 0 and knee fully extension? Well, that's because knee torque has nothing to do with the knee configuration. Again, for the muscle force length curve, it has nothing to do with the length. So when it turns out to be 0 when it reaches the maximum contraction speed, right? So this could be 0 without relationship with the leg strengthening. And then whenever leg is straightened, usually then the next step is you take off, right? So we set the two conditions, like either knee torque is going to be 0 or leg fully extended as a termination condition here. Okay, so when your integration has been terminated, then you could find out what's going to be the corresponding height and distance from the simple ballistic motion formula, kinematics formula. And the next step is you have to interpret the results. Is that really support your hypothesis? Like your specific combinations of V naught and theta naught will give you the maximum height or maximum distance. And then also you examine, are those really compatible to the human data, and etc. Okay. Okay, one final thing I'd like to mention is here there are many parameters that you have to set, because for passive dynamic walking, you could simply formulate it only the body parameter, but here are many parameters to be involved for the muscle mechanics. So there are ways that you can set the parameters, such as the three techniques that I'm going to introduce. So for example, you have to blend the subjective data for in real, you are running many experiments for many subjects, and you could include those data for the averaging. So usually I would recommend for normalization for the height as a length as a height, and force as a body weight, and time as length divided by the gravity square root. For the motor parameters, sometimes you have to refer the previous literature, like how the similar studies set it up the values, or how are some muscle physiological studies been done on it. And often you can't really find the exact case that you can just directly refer to. So in that case, you should do some assumptions. Like for example, if you find a certain value for the typical male athlete, And maybe those are different body part. Maybe then you can sort of do some tuning about reducing some scaling factor that will reflect your interest joint, like a knee joint motion. And for example, you have to figure that out what's gonna be the maximum shortening velocity. And maybe for some previous studies showed about the standing jumping case. Okay. However, it's a standing jumping, and then you are actually doing the takeoff, right? So maybe you're less loaded. Your knee is less loaded case, so maybe your contraction speed should reach further. So in this case, you can actually double those values. Those are all the assumptions that you can refer when you set the model parameters. Again, you can refer to the previous studies research and also put some reasonable assumptions on that. And later, when you are doing the result interpretation, you should do the parameter study about your assumptions made and whether your assumptions are valid or does the assumption affect your main claim. Like here's the optimality. So these are the brief step for the simulation and the parameter selection. For the next time, we are going to talk about how we can solve it using numerical solver like a MATLAB.